We've sent a spacecraft past Pluto, 3 billion miles from home, and gotten crisp, close-up photos of a tiny world nobody had ever seen clearly before. But here's the part that doesn't add up. No spacecraft has ever flown right up next to the Sun, our closest star, the thing 8 light-minutes away. And it's not because the heat is the real problem. It's something else entirely, something built into the basic physics of how everything in the solar system moves, and once you get it, you'll never look at a rocket launch the same way again. Let's start with Pluto, because it actually makes the puzzle worse before it makes sense. Back in January 2006, a probe called New Horizons left Earth faster than anything humans had ever launched, something like 36,000 miles an hour right out of the gate. 9 hours later it had already crossed the Moon's orbit, a trip that took the Apollo astronauts 3 full days. Then, about a year into the mission, it swung past Jupiter and used the planet's own gravity like a slingshot, picking up another 9,000 miles an hour for free. No extra fuel burned, no engines firing, just physics quietly doing the work while the spacecraft coasted through. By the time New Horizons finally reached Pluto in July 2015, 9.5 years after launch, it screamed past at over 30,000 miles an hour, so fast it couldn't even slow down to enter orbit around it. It just took its photos on the fly and kept going, out into the Kuiper belt. So think about that for a second. We built something fast enough, patient enough, and precise enough to thread a needle 3 billion miles away and hit a target that, from Earth, looks smaller than a grain of sand held at arm's length. And yet the Sun, the single most massive object in our entire solar system, holding about 99.8% of everything's mass combined, the thing whose gravity is the reason Pluto orbits out there at all, has never had a spacecraft fly right up to its surface the way New Horizons flew past Pluto's. Here's the reveal, and it's genuinely one of those facts that breaks your brain a little the first time you hear it. It actually takes roughly 55 times more energy to send something to the Sun than it does to send something to Mars. Not to escape the solar system entirely. Not to reach some distant, dark edge of everything we know. Just to go toward the closest star we have, the one that's already right there, lighting up your sky every single day. 55 times more. The reason comes down to something most of us never think about, because we don't feel it happening. Right now, wherever you're sitting, you're on a planet moving sideways around the Sun at roughly 67,000 miles an hour. Not toward the Sun, not away from it. Sideways. Earth has been doing this loop for about 4.5 billion years, and that sideways motion is the only reason we're not slowly spiraling into the Sun's gravity well the way a coin spirals down one of those donation funnels at a museum. Cancel that sideways motion, and down you go. So picture yourself as an engineer trying to send a probe straight into the Sun. You point your rocket at it and fire the engines. Sounds simple enough. Except your rocket never actually loses that sideways momentum just because you pointed it a different direction. Even after a massive burn, it's still moving sideways almost as fast as it was on the launch pad, just now it's also drifting toward the Sun a little. The result isn't a clean plunge into the star at all. It's a new, weird, elongated orbit that swings in close and then slingshots back out, missing entirely. To actually hit the Sun, you don't just need to add speed toward it. You need to cancel out almost all of that sideways speed first, and canceling speed, it turns out, costs just as much fuel as adding it. Now compare that to escaping the solar system completely, which sounds on paper like it should be the harder job by far. Voyager 1, launched back in 1977, is now billions of miles away in interstellar space, further from home than anything humans have ever built or sent. And to pull that off, it only needed to boost its speed by around 40% above Earth's existing orbital velocity. Just speed up a bit more in the direction you're already traveling, and the Sun's gravity does less and less work holding you back the farther out you get, until eventually you're free entirely. Diving into the Sun demands almost the exact opposite, erasing basically all of your existing velocity instead of adding to it. In pure delta-v terms, the fuel budget every mission planner has to work with, it is genuinely, measurably cheaper to leave the solar system forever than it is to fall into its own star. This is exactly why every real Sun mission has had to get clever instead of just pointing and firing. Long before Parker's solar probe, a spacecraft called Helios 2 held the closest approach record back in April 1976, getting within about 27 million miles of the Sun's surface using nothing but a hefty initial trajectory. It stood as the record holder for over 4 decades, which tells you how genuinely difficult even a modest close pass turned out to be. NASA's Parker Solar Probe, launched in August 2018, was built to smash that record by an order of magnitude, and its answer to the sideways speed problem was patience rather than raw power. Instead of trying to cancel Earth's sideways motion all at once with one enormous burn, it used 7 separate flybys of Venus spread out over about 6 years, each one stealing a little bit of Venus's orbital energy to shed more and more of its own sideways speed. Slowly, pass by pass, Parker's orbit tightened, dragging it closer and closer to the Sun with every single loop, the way you'd slowly wind a yo-yo string tighter instead of yanking it all at once. On December 24, 2024, all of that patience finally paid off. Parker swept within 3.8 million miles of the Sun's visible surface, closer than any human-made object in history, moving at roughly 430,000 miles an hour, the fastest anything built by humans has ever traveled. For a second, actually sit with that speed. Fast enough to get from New York to Tokyo in under a minute. Fast enough to circle the entire Earth in about 3.5 minutes. And here's the part that ties the whole thing together. Even at 430,000 miles an hour, even after 6 years of orbital chess played against Venus, Parker still isn't orbiting the Sun the way New Horizons flew past Pluto. It can't slow down and hover anywhere near it. It has to keep skimming through the outer solar atmosphere at that insane speed, again and again, on each pass, because the instant it truly cancelled its sideways motion, there'd be no coming back. Getting close to a star isn't a one-time arrival you check off a list. It's a controlled, repeated near-miss, engineered down to the exact second. Keeping the spacecraft alive during those passes is its own separate miracle. Parker carries a carbon-composite heat shield a little over 2 meters wide, angled to keep its sun-facing surface pointed exactly toward the star at all times, even though radio commands from Earth take too long to arrive to help in the moment. That shield reaches temperatures well over 1,000 degrees Celsius on the sunward side, while the instruments tucked just behind it, in its shadow, stay close to room temperature. It's less a spacecraft and more a tiny, protected shelter riding a wave of solar fire. To put a hard number on just how extreme all of this is, one back-of-envelope estimate for launching a probe on a direct plunge straight into the Sun, no gravity assists, no clever orbital patience, worked out to something like a Saturn V-class rocket, roughly 3,000 tons of machine, capable of putting maybe a couple hundred pounds on a genuine collision course with the Sun, at a cost north of $1 billion. That's the kind of hardware that once sent astronauts all the way to the Moon, reduced to flinging a payload smaller than a carry-on suitcase into our own star. Reaching Pluto, by comparison, took a fraction of that mass and fuel, helped along by nothing more than Jupiter's gravity doing the heavy lifting for free, at a point in the trip where the spacecraft needed to speed up rather than slow down. There's another wrinkle to this that most people never hear about, which is that Mercury, the actual closest planet to the Sun, is almost as brutal to reach as the Sun itself, for exactly the same reason. Mercury is deep in the Sun's gravity well and moving around it at nearly 30 miles a second, so any spacecraft headed there has to cancel out an enormous amount of sideways speed just to slow into orbit rather than fly straight past. That's part of why only 3 spacecraft in history, Mariner 10 in the 1970s, Messenger decades later, and Bepi-Colombo more recently, have ever even made it close to Mercury, and only one of those, Messenger, has actually managed to settle into a stable orbit around it, compared to the dozens of missions that have visited Mars. The pattern holds everywhere you look. It isn't how far away something is that decides how hard it is to reach. It's how fast that something is already moving around the Sun, and in which direction, relative to where you're trying to go. That's also why gravity assists feel almost like cheating once you understand them properly. When New Horizons swung past Jupiter, it wasn't stealing energy from nowhere. It was borrowing a tiny, immeasurable fraction of Jupiter's own orbital momentum, the same way skimming close to a moving truck and grabbing its bumper for a second would give you a shove forward. Jupiter is so enormous that the energy it handed over barely registered as a change in its own motion, a slowdown so tiny it's essentially unmeasurable, while New Horizons walked away roughly 9,000 miles an hour faster. Parker's solar probe used that same trick in reverse. Instead of grabbing a boost from Venus, it handed momentum back to the planet on each pass, quietly bleeding off sideways speed 7 separate times until its own orbit finally threaded close enough to the Sun to make history. So the next time someone tells you space exploration is really just about building bigger engines and going faster, this is the counterexample worth keeping in your back pocket. Distance isn't actually the enemy out there. Motion is. Pluto sits nearly 6 billion miles away at its farthest point, and we reached it in under a decade, using the planets themselves to pull us along for free. The Sun sits 8 light minutes from wherever you're standing right now, close enough that its light left just a few minutes ago, and we've spent over 60 years of the space age just learning how to sneak up on it without getting flung right back out into the dark. Parker's solar probe is still out there right now, still looping, still shaving its orbit a little tighter with every pass it makes around the star that made all of this possible in the first place. Its extended mission is mapped out through at least 2029, with more record-close passes planned at that same 3.8 million-mile distance, each one gathering fresh data on the solar wind and the strange magnetic snapbacks scientists call switchbacks, phenomena we genuinely didn't understand well until Parker started flying close enough to measure them directly. If a spacecraft with a heat shield the size of a small room, skimming through actual solar plasma at nearly 700,000 kilometers an hour, doesn't earn a subscribe on this channel, honestly, I don't know what would. Stick around, because the next time Parker edges even closer and breaks its own record again, we'll be right here explaining exactly how it managed to pull it off.